We lost your voice already. So what's happening? We can't hear you anymore. Is it from my side? Can you hear me, people?
Yes, we can hear you. Mr.
Okay.
Olayinka Yusuf, can you please recap what you said before?
Maybe he lost it. I think it's house. I think he has problem with his connection. Mr. Ismail, you also raise up your hand. You can have your time now.
Thank you, Prof, for the wonderful presentation. Thank you. It's very benefiting. I have two forms of question. The first one is that I've been using WEKA for a while, but suddenly I just discovered that whenever I try to input data, it just writes reading from file underneath, but no file will be read for the analysis and the likes. I don't know what could be the cause of that. So I've tried the method, uninstalling it, and the other things. So I don't know the problem. So the second question is that
for your first question, can you get closer to the mic, please, and repeat the question? You said you use WEKA, but suddenly, what's the problem you are experiencing?
So the problem is that my WEKA is no more reading the file. So whenever I try to read the file, to input the file, it just have reading from file underneath, but no file will be read for the analysis and the other things. So I don't know what could be the cause of that. So that's the first question.
No file will be read for the analysis? Which kind of analysis?
Yes, no file will be read. Yes, exactly.
You mean when you input your CSV file, it will not detect it?
Yes, exactly, sir.
Okay. Question two.
Okay. So the second question is that before this incident, I've been running some file as well, but what I discovered that, so though I was using the Python on the Google Colab, but anytime I try to tune the hyperparameters or to use maybe the smooth, I discovered that the accuracy result I'm having is always getting lesser. When I use the original data, as an example now, in the first instance, when I use the original data, I got around maybe 89.7 accuracy. So when I try to use the smooth, because I discovered that there's a kind of imbalance data. So I use smooth, I use Adasin, but the results, the accuracy got lower to maybe something like a 70 and 60 in some cases. So I tuned some hyperparameter as well. The result was still lesser than the original 80%. So I don't understand what could be my error so that I'm able to solve the problem.
That's my aim for that question. And happy to know that that makes a lot of effort towards learning and also implement. Regarding question one, having problem with your WEKA, what I can suggest is to you, try to, if the problem persists, you can uninstall it. Okay, you can uninstall your WEKA and then reinstall the maybe updated version. You can go to the website and download a new update. Sometimes, if some of the file got corrupted, so this can be called because installation file, maybe mistakenly there could be virus attack on your machine. Anything could be responsible that some of the file may not be corrupted. In that case, you need to reinstall it. Often than not, it do solve the problem. Or restart your machine. You may not have to start with reinstalling. Just restart your machine. Sometimes when you start machine, it's an environment where there's electricity. For weeks, we keep our machine running. We just get it to sleep and wake it up again, continue working. So this plug some of the files are plugged together. So restart your machine. Hopefully the problem is solved. Otherwise, reinstall it. Hopefully that should solve the problem. Regarding the second question, see, when you do modeling, we have to pay attention to the fact that the moment you start using smooth on your data set, you are using a different data. You are not using the original data anymore. So that's why if the result kept getting bad, it means Smooth does not work for that data. It means the original data is getting better results, so you better stick to the original data. There's what I call generalized procedure. Hopefully, there's a general guide that will be out soon, by the grace of God. Letting the data speak is very important. See, when you do modeling, the procedure is this. The procedure is this. You start with the original data. Your original data. Always start with it. This is what called the principle of let the data speak. I believe you are solving application problem, Mr. Ismail. That's why you are using small. Am I right?
Yes, sir.
Okay.
It's correct, sir.
Okay, because if it is regression problem, we don't need small because we do have imbalanced data in regression. Now, use the original data set, the one that came to you directly. Do your modeling with deeper parameter, see the results, you are getting 89 or 80-something%. Then do hyperparameter, like the case of SMOREG we discussed today, or SVM. Change the polynomial. The most important hyperparameter in support vector machine is polynomial. It's kernel. Check the kernel function. Check different one: poly, PUK, Gaussian. The one that gets you the best result. Go to C, the regularization factor C. Do the hyperparameter value structure also for it, and others. Once you arrive at that, by that time maybe you are going to be getting 96 or 98. See, you are doing fine. However, because you notice there's imbalance in the data, maybe I'm stuck at 92% finally here. Then I might try to do the smooth. Smooth is try to do the balancing. It's try to balance your data because the data is imbalanced. You notice that smooth is generating 68%. But take note, when you do smooth, there's this mistake people also make. The same hyperparameter you have gotten here may not be good for the smooth because the smooth is having a different data set. After you run the smooth, it has changed the number of samples. Because if you are having like class 1 used to be 60, while class 2 used to be like 200 sample. You balance it using smooth, it makes it to become, this one becomes 200, this one becomes 200. It means we have additional 140 data set coming in from nowhere using smooth idea. So this data is different from what we started with. The hyperparameter optimization has to be done again for this new data. So when after using smooth, you have to do hyperparameter only because the hyperparameter might not work. The one you use here, the value, maybe polynomial is working. It may be Gaussian that will work for the smooth. So you have to do the hyperparameter again. This may be the reason why your result kept getting bad and bad after the using the smooth. Because we have to know that after using smooth, you are working with a different data set. Because the data set is now more than what we started with. That's why when you have imbalance, I usually prefer that you do the undersampling first. Reduce this 200 to become 60. So you have 60, 60, and do the modeling. Of course, also you have to do the hyperparameter optimization. It means your hyperparameter optimization will have to be done 3 times. For the original data, for the undersampling, and for the oversampling using smooth, where you're going to increase the minority class to become like the majority class. While in the case of undersampling, you are reducing the majority class to become also like the minority. In each case, there's need for different hyperparameter optimization. So following this, I want to believe your results to get hopefully better. Sometimes smooth does not give you the best. Undersampling did not give you the best. It is the original data that might give you the best. There are cases like that. That's why I said, let the data speak. Some people believe smooth should give me the best. No, it depends on the data set. We have modeled different data sets where smooth work for us. And we've had cases whereby, even though there's imbalance, the best result was gotten from original sample. So let's put this in mind and always let the data speak. Thank you. Mr. Hassan Isiaka, you can ask your number and your question. Mr. Hassan Isiaka.
Assalamu alaikum, Prof. Can you hear me, Prof?
Yeah, can you clearly?
Okay. Good morning, sir, and thank you for this class. We are really grateful. Yeah.
Please unmute yourself because somebody was talking. I unmuted everybody.
Okay. Now, Prof, in a situation where you want to predict an output, and the output is more than one instance, like you have 2 to 3 outputs you want to predict, is it possible to have a single model that can predict these 2 or 3 outputs simultaneously?
Okay.
You see?
One by one. Even doing modeling for one, it's not easy for us to get better results. So putting them together is not possible. If you are writing code in Python, we can write a code that will put all of them. We write different looping after this, do this, but each one will have to be modeled separately. But we can write it in a code form that we just click run. It will run all the models at the same time. However, each model is being built separately. For example, I want to predict Y1, Y2, Y3. They are all in the Excel. I have to put them separately, build for Y1, build for Y2, build for Y3. There's no model that can generalize a single model that can work for 2 different variables. It's impossible. So you have to do them one by one. So that is it. Okay, taking Mr. Anyila Olatunji Mutiu.
Assalamu alaikum, Prof.
Alaikum salam.
Yes, we are indeed grateful for this opportunity, laudable opportunity.
You're welcome.
Given this, yes, but the problem I usually have is when you attempt to use WEKA, or when you are using WEKA and you are dealing with a data set that is very big. So memory storage, that's the issue. Having memory issue in running a data set that is a little bit big. So I don't know how to go about it.
One, it depends on the power of the machine. Yeah. In data science, this is a big issue. So that's why people are going to GPU. Yeah. So the moment you start transitioning to working with big data, then you may have to, one, there are different options to this. Either you have to start trying to use Google Colab, where you can have free access to GPU on their platform. This is one. Two, for a proof of concept, you can try to draw down the data set. You have a very big data you want to work with. Can you take a sample of this data, at least to check it on WEKA and see if it's really going to work? Yeah, if it is working, part of those data set is working, then you can then start to see, okay, maybe I need to obtain a new machine. You may have to buy a better, actually laptop is not an ideal system for modeling because of the low power. Sometimes it gets heated up and shut down. So sometimes you might have to run for hours. So desktop, if there is stable power, is the best. You have a very powerful desktop and you don't run anything with it. Restart your machine before you start. Sometimes we open, this is just a kind of some suggestion for us to effectively utilize the available limited resources. Sometimes we open a browser with several tabs, 15, 20 tabs on a single browser. This is taking a lot of your memory. We might not know. You have Microsoft Word documents open, like 15 of them or 10 of them. They are taking huge memory actually. So try to close down all these kind of tab you are not using, any other window file you are not using, so that you make sure you are running maybe the WEKA alone and few very important other files. Hopefully, this may assist you to be able to effectively utilize your available resources. And then the memory of your machine also, it depends on the memory of your machine. Using laptop with just 4 GB, 8 GB, they are getting smaller. Even Windows alone, we use majority of this GB. If somebody installed Windows on 4 GB machine, can assure you, you don't have anything like after Windows, which Windows just released recently, Windows 10 or Windows 11 or the once they are on, they're taking over the whole memory. Before you even launch WEKA, your memory is almost full. So you need 16 GB, 20, 32 GB, and more powerful memory capability for your machine to be able to do the model. So for the start, you can reduce the number of samples you have, play with it, cut it down to half, try to work with it. There's nothing bad in that until you are able to have facility that will take care of the available data, either by buying a desktop is very powerful and you dedicate it to running your model. And then you may have to go online for free GPUs or subscription GPU. I hope that answers your concern. Ayla.
Yes, thank you. Thank you, Prof.
You're welcome. Mr. Yinka Yusuf.
Okay, thank you so much, sir. Yeah, I'm back, sir. I'm really sorry. I don't know what happened the other time. I kept talking, but I didn't realize that maybe you had stopped hearing me or something. I said I was going to seek a clarification and then also ask a question. So, as regards the clarification.
Okay. Okay, can you come again, please, with your question? Sorry. I think we lost Mr. Olanyika again. Am I right? So
yes, no, I think Triple A can continue.
So, Triple A.
Hello, Prof. Sir. Prof, sir, I'm back, sir. Okay. Prof, I'm back, sir. I think I knew what the problem is. So it's from my end. I hope it's not going to happen again. I'm so sorry about that, sir. It's from my phone. So firstly, yes, sir. So I was talking about the performance metrics that you mentioned, and I said that you did mention you recommended mostly out of the several that are available, correlation, and then the use of the RMSE. Then I said that in the formula that you showed on the slide, it showed R squared. And I said that I understood that to mean coefficient of determination, which explains the variations that are accounted for by the independent variables or the predictor variables in a regression analysis. So I was now trying to ask that, is this actually the R squared we are using for that interpretation as a performance metrics, or the correlation as we mentioned it? Because also when you ran the WEKA, as we saw it, it was correlation that was actually written there. So I was trying to seek a clarification on that. So that was the first thing I mentioned. Then the question I wanted to answer actually, the question I want to ask really has to do with, I said that as we are running the analysis and as the lecture was ongoing, what kept coming to my mind is what is actually the difference between the traditional regression analysis that I can run, for instance, on SPSS, or I can run on Starter, for instance, and then the use of machine learning model or machine learning algorithm for the same analysis. Because I looked at it and I said that there really has to be something that would be really different. And as you presented the charts of the predicted value and also the actual value, it occurred to me that, okay, maybe traditional analysis might not be able to do that, but I don't want to assume. I want to learn more by understanding the actual differences that can give edge to machine learning algorithm as against the traditional regression analysis that one may be able to run with SPSS. Maybe even for this kind of data set you used, that what would have happened if it had been done with a traditional, regression analysis with the use of SPSS, for instance. Thank you, sir.
Okay, thank you, Olanyika Yusuf, for that, for those questioning. Yes, regarding the first question, yes, it was correlation coefficient, okay? Yeah, so it was correlation coefficient, as you can see in the WEKA as it is displayed. So we have to actually check out what is being used in our own area of specialization. Yeah, and then we use it accordingly. And there are other, we can check, we can decide to add more performance metric depending on the problem we are solving. The second question you asked, yeah, there's a big difference between the modeling in machine learning and the traditional statistical modeling. One of the big difference is this. In fact, there is one of our paper whereby one of my friend professor, I think I showed in the presentation during the training, in the summer training program. You see, the SPSS do a situation whereby you divide the data into two. It only works on that one data. You see, the data that you have, then you can do regression analysis for it. Then to now keep a testing set separately, and then you bring it in and then get the result. You don't have that in the classical statistical model. See, this is a big changer that the big change system that machine learning has brought on board. That you can train a system, we call it training set, the 70% for training. After the training, we give the 30% to the system. Without seeing it before, it will estimate what's supposed to be the outcome, and we not compare the result that we know with us. And we can see if we train it very well, we can see that the outcome is going to be very close together. And like the cases I actually showed before, you can imagine this having a regression solution like this. Instead of going to laboratory, you have a machine learning model that can predict exactly what you will have gotten from laboratory like this. Because this is near 100% prediction. No mistake. It's not far away. Here, there's a few, very little difference between the experimental and the predicted value. So if we can train a system that after more training and validation, it consistently predicting the exact value that we are supposed to get from the laboratory, then we can then tell our chemistry professor that, hey, prof, no need to spend several weeks in the laboratory. Our machine learning algorithm will do this for you. And if we are not able to get a single model that can do that for us, we go ensemble. We try to get several machines together, several ensemble models, get them together. We give us better result that anytime you run it, you can be sure that you're going to get 100% accuracy or correlation. Even exact value you are expecting is what you are going to get. So this is the big difference from the classical statistical modeling that we have. Then when we bring in the big data analytics, in statistics, we feel another big difference in statistical modeling and machine learning modeling. In statistical modeling, you model data that is frozen. You have to freeze the data. You have to freeze the data. Then you can use the statistical SPSS on it. However, these days, we want modeling on the go. On the go. That's what we call big data. One of the characteristics of big data is velocity. Velocity. It's moving data. It has been noticed that statistical modeling cannot undo moving data. You have to freeze the data before you can apply statistical analysis. But machine learning has that capability of modeling the data while it is in motion. For example, you are using Google Drive. You arrive at a particular city. Google Drive will alert those people who subscribe to you. Yeah, somebody is traveling, is now in city A. Can you send him advertisement? Immediately they start sending you advertisement. You start receiving advertisement. There's a promotion in so shopping mall close to your hotel, close to you. If they delay it, if they have to freeze the data for modeling, maybe by that time you'll be in city B. By the time you are in city B, now they are starting the modeling because they have to download the data, freeze it, and then start modeling using statistical modeling. By that time, you are getting promotional sale when you are in city B, but the promotional sale is about city A. we can see that at that point it doesn't make sense. The business already lose the opportunity of getting a customer because you left the city already. So we need a system that can model why the data is in motion. And that is machine learning is able to do that. And that was the big breakthrough that machine learning brought to data science. Data science is not new. Statistical modeling has been in use for data science for since time immemorial. However, with the increase in the size of data, there's no time to download all the data. We work in the cloud. Everything is to be done in the cloud as it is happening. So this is one of the areas that you have to take note that differentiate between machine learning and statistical modeling. But for a layman, you can have testing sets and validating sets that has never been seen by the model. You can then use it to estimate it, which is not applicable to the case of SVM modeling. We use SPSS on the complete data and we show our results. But in case of machine learning, we say data that has not been seen before. We can deploy it to online. You can predict who's going to be absent tomorrow, who's not going to come to work, which staff may resign in the next few days. What's going to be the market price for next week? Is it going to be rain? Is it likely to be erosion? Or is that going to be flood? Things that have never happened, we want to be able to have an estimation of it. This is not possible for statistical modeling. These are things that machine learning are able to do. Let me clarify that answer your question.
Prof, I'm very, very glad with the extent of the clarification explanation. It has become clearer to me now the kind of nuances that I was expecting. But another area still troubling me in my mind, permit me, sir, if I can mention it, okay. It is usually said that I'm a lecturer and I teach statistics, research method, and things like that. And one of the things that we usually tell our students is that correlation does not imply causation. That variable A correlates with variable B does not imply that a unit change in variable A is accounted for by that variable B. So that is why we usually advise, if you do correlation analysis, go a step further to do regression analysis so that you can actually account for variables that are responsible for the variation, in the dependent variable you are trying to explain. Now, so I haven't said that, I haven't known that. So why is it that this still correlation that we are using as a performance metrics for decision making when it comes to the strength of a model in machine learning model? I think, I don't know if I'm able to explain that very well, but that is just what came to my mind again that I've been thinking about. Thank you, sir.
Thank you very much for your question. I like the intuitiveness and then also following up. Actually, this is why, if you notice, we know the limitation of correlation. It's well aware of in machine learning modeling circuit. However, it has its own advantage, but you don't use it alone. Thank you very much for this question. Let me mention that. You don't use correlation alone to measure the performance of your model. You'll be messing up with yourself by doing that. You get the point. You see? And you can see it in let me show us what we just did in the Excel. You can see this Excel. You can see how we're already getting 99% correlation. However, you can still see that a lot of values are not really close to what we want to estimate. That's why, you are right. You can see 63, 62. It's okay, it's close. 520, that's still far away. This is why, but correlation implicates that the data trend is that as this one is increasing, this one also is increasing. As this one is increasing, this also is increasing at almost some little relative rate. However, you are not expected to use only one performance measure to judge any machine learning model. If you use it, that kind of report or paper is going to be rejected because every performance measure or metric has its own disadvantage. That's why we do use at least two. Correlation coefficient is there. And then in addition to that, you have to have the root mean square error or percentage error or whatever option. For me, I do use the root mean square because the root mean square error will show us the exact error that is being committed. Look at it here. 5.8 means there are still some predictions that are not in the way it should be, even though our correlation coefficient is already 99%. At 99%, we can go to sleep because we think we're already getting 100%. This is why we don't use correlation, but we use it to guide other performance measures. For example, we are getting 0.5 correlation. If you check the modeling, you see that the model is going to be really, really bad because it means the prediction of the actual system. But we don't check correlation alone and go to rest, but rather we have to combine it with other performance measures. And that's why you can see how many that WEKA has produced. And you can add more. You can decide to add more performance measures. Use the prediction plot to see exactly what value you are predicting. Are they close to it, irrespective of the correlation? I want to see it physically, how close they are to the expected value. That's why we combine all these things. Even after using root mean square error, after using correlation coefficient, you are expected to make plot. Like the examples I've shown here, that can show us how are you doing. Tell me the prediction, the difference between your prediction and the estimated value. I hope that clarified, Mr. Olayinka and the
I'm very, very okay now, sir. Very, 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 very clear, sir. Thank you so much, sir.
You're welcome. Thank you. So now we answer one or two questions from the audience. Somebody says, why is there no confusion matrix in the regression problem? Well, because if you look at the confusion matrix is try to look at where did you false positive, false negative. We don't have that in regression because we are predicting numbers. See here, this is positive. 20. This is false. This is true positive, true negative. This one is false positive. This is false negative. You see? So here you are saying that something is positive, meanwhile it's not positive. We don't have that in regression because we are predicting numbers. But in classification, we are classifying objects into air, go air, go air, go air. You are sick, you're not sick. When you say something, somebody who is sick is not sick, that is false negative. When you say somebody is sick and is not sick, that is called positive. So we don't have that in the case of regression because we are predicting actual value. Hopefully that's question. And last but not the least here, can you guide me on how to get install WEKA? Somebody can help us share the link to install WEKA. We shared with us during the last summer training. So you can also go online. You can just say WEKA download. Then you specify if you are using Mac machine or you are using Windows machine. How do we?
The link is already on the chat box, Prof.
Okay, thank you very much. How do we know there is overfitting during optimizing the hyperparameter? Yeah, thank you very much. The way you know there's overfitting is the characteristic of overfitting modeling is your training set performance will be good, but your testing set will be bad. This is how you know. You're going to get it very bad. The training set will be like 99% correct, either in classification or in regression. Your error will be very low in training because it has memorized it. But when you have the testing set, the performance will go down. For example, you're having like during testing, during training, you check the results. So you're having like 90% performance, or let's say 95% accuracy, let's say for classification. But when you go to testing, you suddenly start getting 30% correct. The gap is too much. We want a system that has the difference between the training and the testing should be low. In fact, we want your testing set to perform better than training set. Because we want to use this on same data in the future. And we want to be able to cross our prediction. So the moment you are having a training set performance that is 95%, or sometimes you have 100%, by the way. And the moment you get 100% your training, you should be afraid that it might likely be memorized system. It has memorized all the training sets. But when you bring in the testing set, it's getting 30%. That is overfitting. You go back to the drawing board and fit the upper parameter optimization until you get the appropriate conclusion. And that is why in WEKA make life easy for you. WEKA ordinarily will not even show you the training set. It only show you the testing set. So the moment your testing set is not good, you keep trying to make it better. That is WEKA for you. But if you want to see the training set, then you have to go back to more option and say, show me the training output you can see here. It doesn't, by default, it doesn't show you your training plate because it's a waste of time. Because until your testing set is good, you should not stop. But training set, when you show you your training set, some people just see the training set and started celebrating. Oh, I'm getting 99%, but the testing set is bad. Because the training set is huge, it's 70% of the data, while the testing set is small. So you see more of the training set on the screen, and it's celebrating me while the testing set is not good. So this is why, usually by default, WEKA does not show you the training set. But if you want to see it, you can go inside, and then you can see it. I hope that clarified that question. I believe that is those questions we have for the day, and our time also is fast spent. Thank you very much all for coming.